So let me also join in first thanking the organizers, in particular Mario Schmierek, for setting up this wonderful event and workshop, and we had a nice dinner yesterday, so thanks. I would also like to really express my deep gratitude towards Eli Stein. I think I'm surely one among the many who really very strongly benefited from Eli's visions, mathematical visions, and personal support over many, many years. I still remember the wonderful time at the Institute in Princeton, and also the long series of lectures of workshops which I had the privilege to co-organize with Eli at Oberwolfach over so many years. So thank you very much, Eli. So the title of my talk is Fourier restriction theorem for a non-quadratic hyperbolic surface. So what is the background of this problem? There has been a lot of work on Fourier restriction to elliptic hypersurfaces, so something like spheres or paraboloids, and also conic surfaces, where the second fundamental form is positive definite, let's say. But there's surprisingly little really known about hyperbolic kind of surfaces, where you still have non-vanishing Gaussian curvature, but maybe some principal curvature are positive and some others are negative. And so we'll maybe first briefly review some of the results which are known, and then very quickly specify to some situation of a two-dimensional specific hypersurface, which we have been recently studied with Stefan Buschenhenke and Anna Vargas, and that's part of a bigger project. Eventually, we would like to really understand much more general situations where you have positive and negative curvatures also in higher dimensions. And at least we are now happy that we have the first results, which maybe at least give some idea what's going on geometrically in such a situation. And I think, as we all learned also from Eli, you should first look into examples. And so this is just a very particular example, but I think we learned quite a lot. So, as I said, let me first briefly maybe review a little bit what this is about. So the concept of Fourier restriction had already been introduced, for instance, in Fulvio Ricci's talk. So we're looking for a priori estimates of restriction of the Fourier transform of a function and LP of Rn to some hypersurface S, and in terms of the LQ norm with respect to some surface measure. And if you have such an estimate like 1, then of course this yields a bounded restriction operator R from LP of Rn to LQ of the hypersurface S, let's say, with respect to the surface measure d mu. And so the whole story began a long time ago with very important work by Eli Stein, Pfefferman-Stein, Zygmunt, Carlsson, and so on for curves. That was the first case, and then the celebrated Stein-Thomas estimates, which were LP-L2 estimates, were very influential. And then more and more sophisticated methods had been developed. So I just want to mention very few names, influential, which had some great impact on these developments. So there was work by Bourgon, Wolf, Muya, Vargas, Vega, Tau, where the so-called bilinear method was developed through induction on scales and wave packet decompositions. Then further improvement came through the method which was initiated effectively by work by Bennett, Carber, and Tau on multilinear restriction in Kakeya estimates, and then was applied in work by Bourgon, Guth, and many others ever since then. And more lately also, the so-called polynomial partition method became very relevant and has turned out to be a very powerful new tool. And so the names to be mentioned is Dwyer, which did, let's say, finite field Kakeya, and then Guth and Katz, and many more, right? So, but I don't want to really go into that. And so what we thought, we start again with the bilinear method, just to see what geometrically happens in the case of some negative curvature. So, as I said, from now on, I will just concentrate on two-dimensional surface, so everything will be quite explicit. So we have a two-dimensional hypersurface S in R3. And as I said, ellipticity basically means that the second fundamental form is strictly positive. And let me first review what is known about this situation and then compare to what is known in non-elliptic situations with a non-vanishing Gaussian curvature. And so the first step usually is that one passes from the restriction operator to its adjoint operator, the so-called Fourier extension operator, script E, which is basically just given by, you take a function f on the surface multiplied with this density, let's say the surface measure if you have a compact surface, and take its Fourier transform. And then what you really want to know is what kind of LQ to LP estimates this Fourier extension operator will satisfy. And if possible, to determine the maximal optimal range of pairs P and Q for which such an estimate holds true. And so for this elliptic situation, think of a sphere or the paraboloid. The conjecture, Stein's restriction conjecture, states that this inequality, that E of f should be bounded in LP of R3 by the LQ norm of f on the surface, that this should be true for P strictly bigger than 3 and P greater or equal to 2Q prime. So this, the line P equals 2Q prime is a so-called critical line. It's easy to see that this is a necessary condition. And so what is known? Well, I mean, the so-called bilinear method, which I was already talking about, led through work by Tau to the following fact that if P is strictly bigger than 10 over 3, then indeed this restriction estimate or the extension estimate holds true. So we are still far from 3, but 10 over 3 is not so bad. But for instance, through the polynomial partitioning method, more recently, Guth was able even to push it a little bit further down to 3.25. Okay, so this is for two hypersurfaces which are elliptic. Now let's look at the situation of a hyperbolic surface. So hyperbolic, by hyperbolic I really mean that one principal curvature at each point is positive and one is negative, right? So some kind of set of things. And so the easiest hyperboloid which one can think of is a quadric, which you could take the graph of x squared minus y squared, or if you rotate coordinate, then it looks much nicer even, the graph of x times y. So that's what is written here. And indeed, to the best of our knowledge, this is the only case for which one really has reasonable restriction and extension results. And so this was in separate independent work by Anna Vargas and Sanjuk Lee from 2005, where they proved that for this quadric, so the graph of x times y, indeed if P is strictly bigger than 2 times Q prime, so if you're somewhere way below the critical line, and in the Tau range, if P is bigger than 10 over 3, you indeed do get this kind of restriction estimate. And so this is by Betsy Stovall, when we were in Berkeley, we were informed that she found a way that took quite a while now even to get points on this critical line. So there was a problem in the passage from the so-called bilinear estimates, to which I will come back, to the linear estimates. And she has found a very clever way to really improve the methods by Anna Vargas. And so in that way, she was able now even to get points on the critical line. So that means one has sort of the full analog of Tau's result for elliptic two-surface. And also very recently, there's a paper by two young Koreans, Chow and Lee, which also prove the analog of the corresponding result by Guth for this kind of very special hyperboloid. But the big problem was this was the only case which was known. And I will show later why this case could be treated more easily and what is the problem if you add perturbation terms. So what we really would like to be able to add small perturbation terms of higher order to x times y, and one would expect that one would get the same results. For instance, if you think of the Stein-Thomas type estimates LP2, then what really matters is only the decay of the Fourier transform of the surface measure, And whether you take x squared minus y squared or x squared plus squared doesn't make any difference by the method of stationary phase. You get exactly the same decay. So there's good reason to believe that this should be true. But as I said, not so much was really known. And so we thought, okay, we wanted to understand at least one perturbation. And we took the simplest possible one, where we just add, let's say, to x times y, 1/3 y cubed, right? And of course, we would be interested in the long run in more general perturbations. But it turned out this created quite some differences compared to the classical situation. So this is really the surface, the graph of this function, the graph of this function, phi of xy equals x times y plus 1/3 y cubed. That's the thing which you really want to study. And our recent result is that indeed, for that perturbed hyperboloid, we still have this the right Fourier extension operator estimate. So don't worry, I wrote 2p everywhere in place of p, because this relates better to the bilinear approach later. But just you should think 2p is p, right? I mean some other number. So this is basically the analog of the previous result by Vargas and Lee for the unperturbed. In this situation, to get to even 2 points on the critical line, I think should be even a lot harder. So I mean, this could be very challenging. But anyway, so we almost get this. We're missing points on the critical line. And still we have the tau range, so 2p is bigger than 2/3. So this is by, as I said, by use of the bilinear method. So let me briefly explain, even to those who are not familiar with this bilinear method, what are the main points here, right? And I will just try to compare the classical elliptic situation with this situation here to show what are the differences and points where we need some changes. So the idea is just to establish a so-called bilinear estimate. So you take the extension of a function f1 and multiply it with the extension of a function f2, and you want to have L2, Lp estimates of this kind of bilinear quantity, right? And but the point is that this is under the assumption that our two functions f1 and f2 are supported on two separate pieces of the surface which have a certain kind of transversality. So they should definitely be transversal, these two patches of coordinates, S1 and S2, on which these functions are living. But we'll see a stronger kind of transversality is really needed to apply this bilinear argument. So even without going into this bilinear argument, I will show you the main points, what geometrically happens. So as I said, this kind of transversality can be expressed in the following form. So you have this expression here. So imagine you have two pieces of surface. Imagine also that since the surface is a graph of a function phi, so they're sitting over two patches, u1 and u2 in the R2 in the coordinate plane, so to speak. And a function on the surface we can always view as a function on these two coordinate patches. So f1 lives on u1 and f2 on u2. And so the necessary transversality condition has been worked out by Sanyuk Lee in a paper from 2005. So that's really transversality. And so the result by Lee also says, if you also have an upper control on derivatives of phi, then this automatically leads to leads to good bilinear estimates. Okay? So let me just at least briefly indicate, maybe the light is it here? Okay. So let me briefly indicate what this really geometrically means, if you haven't seen that condition. So suppose you have your two surfaces. So you have a piece of surface here. And you have another one which is transversal, but I have already translated that. I hope I can draw this properly. So suppose here this is maybe your patch of coordinate of surface S2, and you have another patch of piece of surface S1. So this is this piece here and this one. Now you translate them so that they intersect, and then you have an intersection curve. This curve here, and then what you do, you take the normals to let's say, to this surface here, for instance. And you view at them along this curve here, right? So you take the normals along this curve. That will give you some cone here. So this, let's say this is a cone gamma 1. And then on the other end, you have the second set of normals coming from, no, sorry, I got confused. So the normals from here, sorry, from the first surface. I should have gone this way here. Okay, so this is the normals corresponding to the first surface. And then the condition geometrically, what you really need in this kind of bilinear argument, which is very important for some kind of counting argument in this argument, is that the second set of normals here, N2, that they are sort of transversal to this cone. So they have to be transversal to the normals of the other type of normals, but even transversal to the cone. So they should not sort of be tangential here horizontally. That has to be avoided. And that's what this condition really means. Okay. So now let's look at the corresponding quantity. So let's introduce the notion TVZ1 of Z2. Z2 of Z1 is this quantity where the point Z before is just at Z1, right? Morally, what we really need that the two quantities TVZ1 of Z2 and TVZ2 of Z1 are bounded from below for all points Z1 in U1 and Z2 in U2. So that's really what this condition means. And now let's look at this quantity for, let's say, elliptic surfaces. In that case, for instance, if you take the paraboloid, you just compute that TVZ2 of Z1 is just the distance of Z1 to Z2 squared. So whenever you have 2 points, so I don't even light things, but I mean if you have two points on your surface, right? Automatically, if they're not the same, they have some separation, have some transversality, and so that means you can later on some argument take little boxes, at least in the coordinate plane here, whose size is comparable to the distance here of these 2 points, and that's really the right decomposition at different scales. And so these pairs of points lead to good transversal coordinate patches. So this is a very classical elliptic situation. Now what happens if we have this really the hyperboloid, the graph of x times y? So this the second case here. In that case, you see that this transversality function factors into two factors, y2 minus y1 and x2 minus x1. So you see, in order to have transversality, your 2 points should be separate in both coordinates. And so that's why Vargas and also Lee did the following thing. If you view this as in the coordinate plane here, if you have a point here and you have a point here, you want to have rectangles later on. And so in this case, what you really need, that the product of these two things here, of the first factor y2 minus y1 and these other transversalities, is bounded from below to have some kind of transversality. That's what it really means. Okay? And but there's some important observation. If you add these two transversalities, you see the differences of the x2 and x1, they cancel, and you just get the product of y, you just get y minus y1 minus y2 squared. And that's quite relevant, because suppose after some scaling in y, that y1, the distance between y1 and y2 is of size 1. Then it tells you that if one of these two transversalities is very small, the other one got to be of size 1. So they cannot both be very small. So that turns out to be an important information which we really use. Okay. So let's see. So what can we do with this? So now, so this suggests to choose situations where this tau z1 of z2 is of a certain size delta 1, tau z2 of z1 of another size delta 2, and the distance between y2 and y1 is of a third size rho, right? So think of these numbers to be dyadic numbers. And we can always, by symmetry, assume that delta 2 is the smaller of the two numbers, so delta 2 is less or equal to delta 1. And what is also interesting and nice in this situation, by translation for this specific surface, you can very easily reduce to the case where Z1 is 0. Because if you translate, so if you look at phi at Z1 plus Z prime, you easily compute that you get this thing here. So if you take this as another coordinate x double prime, and y prime is another coordinate y double prime, you still get phi of x double prime, y double prime, plus some affine linear term, which doesn't matter in this problem. So affine terms don't matter. Okay, so that helps. So from now on, let's just assume that Z1 is 0, because then everything gets even simpler. So in that case, this delta 1 is just that was the size of tau Z1 of Z2 is just mod of x2, and delta 2 is just x2 plus y2 squared, and rho is mod of y2, and the previous estimate leads to the estimate that, or identity leads to the estimate the rho square is bounded from below by roughly delta 1 minus delta 2. And so let me now draw also the picture in this case. So you have again two lines. So now, so suppose our point Z1 sits at the origin in this case. So you have still the horizontal line, which is a line where y2 equals y1, and you have this parabola. And so this is. So these are points where if your second point sits here or here, transversality is 0, because one of the two factors is 0, right? So that's what you want to avoid. So you better stay away from these points and this point, or the points on this line and on this line, right? So that's really what transversality asks you to do. And that's an important difference now. And now you want to ask, so suppose you have 2 points, what kind of boxes would you try to find around them as big as possible, so that on all points within these 2 boxes you have the right transversality at a certain scale. And so we distinguish here 2 cases. If rho squared is much smaller than delta 1, that's case 1 here, then you find from this last estimate that delta 1 and delta 2 must be comparable in size. And so we call delta prime this number, let's say delta 1, and then it's natural to do a 2-parameter scaling. So you write x as delta prime x prime, y as rho times rho y prime, and then if you rescale your phase function properly, so you do the scaling, but you divide here by rho times delta prime, you get this x times y prime plus this cubic term, but now this coefficient in this case is very small. So you really get a very small perturbation of the hyperboloid x times y, and that's fine. So this case behaves pretty much the same way as if you didn't have this perturbation. And so again, you would sort of take rectangles to separate things. And that's something like if your point Z2 would be somewhere here, let's say you would take a long rectangle here and one here, and on those 2 rectangles you would have basically have the same kind of transversality, right? So these are the kind of Whitney boxes which come up in the argument there. But the other case is if rho squared is much bigger than delta 1, let's say at least over 100. And that's a non-classical situation. In that case, it turns out delta 1 is of size rho squared, because again of this previous identity. And now here it's very natural to do a parabolic scaling. So you scale x1, scale that x is rho squared times x prime, and y is rho times y prime. And you scale here properly. And you see under this parabolic scaling, the phase is even invariant. So you get the same phase function phi. And now what you gained is that now x2 prime and y2 prime are both of size 1. And then in this case, if you compute the transversality, tau z2 of z1 in these new coordinates, you find out that you get this is of size delta 2 divided by rho squared. And remember, delta 2 was smaller than delta 1, so this is much smaller, cannot be too big at least, so maybe it's at most 100 or something like that, right? But it can become very small, this number delta. And so there's a subcase, if delta is still bounded from below, let's say by 1 over 100, then still both transversalities after the scaling are of size 1, And then you can again apply Lee's theorem directly and get a good bilinear estimate. So that's again a favorable situation. So what is left is a situation where delta is very small. Let's say delta is smaller than 1/100 or something like that. And in that case, you have the following situation that the one transversality at one point here, this transversality is of size delta, which is very small, and the other one is of size 1. And so that's bad because you have different transversalities. I mean, one is very small, the other is of size 1. And we got stuck for quite a while. We tried some scaling, and so some of the natural scaling is that maybe you want to scale somehow in x2, because let's say the picture here would look a little bit more as follows. So again, so we have this curve, we have the horizontal curve. Here's where Z1 is located. And now after scaling, Z2 sits, let's say a distance, a vertical distance 1, let's say, above Z1. And so what kind of boxes would you naturally take on which the transversalities are of the same size? So the natural things turn out to be really these kind of curved boxes of size delta times 1. And here you're only allowed to go delta delta in each direction. Because if you move too much here in this direction or this, then the transversality could be very small, even 0. Similar if you move vertically here. But here you have a big box of size delta times 1, which is okay. So that's a new situation. So we have one is a curved box, and the other is a very tiny square of size delta times delta. And these are the natural things to do here, right? And so as I said, so now if you're sitting here, sort of you are tempted to scale by delta in this horizontal direction. And indeed, if you do that, so after the scaling, so these are the boxes. So this is what I called U1 and U2, let's say. So this is the box U1, and this is the box U2 here. But it turns out that in order to really have control on everything what you need, the right scaling, as I said, is this scaling. So really you scale in x by delta, that's fine, but of course this pulls things very much apart. So things are getting very long in the horizontal direction. And that took us a time to realize, it's better to scale the function phi by also dividing by delta. But this has the devastating effect that this term becomes extremely big, right? Because it's a 1 over delta times y cubed, so it blows up. And that, at the first glance, is scary, but it turns out this is exactly the right thing to do. And because one thing is easy to check, that after the scaling in the new coordinates, which are called here x bar and y bar, both transversalities are really of size 1. That's what we like to see. And also other conditions which you have to preserve in the bilinear method. I mean, the normals have to move at a certain rate, the angle along the intersection curve, all this works. So this is really the right thing to do. And so in the end, we can prove this kind of bilinear estimates for such two pairs of boxes or curved boxes, U1 and U2. And for instance, we are really interested at the case where p is roughly speaking 5 over a third, and then this exponent is minus 1 over 10th. So there's a blow of this order, delta to the minus 1 over 10th, and this is optimal, this is sharp. And but you see, because of this big term here, the Hessian at one point here, the Hessian determinant is very big, and so we cannot just simply apply Lee's theorem, because the derivatives blow up of size 1 over delta. And so we have to go into the proof. But we have already studied in an earlier paper such similar situations. So this leads to the fact that the tubes in which wave packets are supported have to be of different lengths, so to speak. But just briefly to indicate, so the tubes on which the wave packets corresponding to the first surface, T1 should be of size r times r squared. And the tubes in the other direction should be shorter by a factor delta in the long direction, right? And so when you do that, in the end, the argument still goes through. So you have to go through the bilinear argument, but it works. And that's how we get this bilinear estimate. Okay, as I said, there are also other technical issues. For instance, the basis of the induction of scales requires some refinements and so on, but I don't want to go into these details. But anyway, so we get a favorable bilinear estimate under these situations. But now you're in this weird situation that you have to take pairs of sets U1 and U2, which have this quite different shape. And then you have to see if in the passage from bilinear to linear, how to group things together to end up with the right estimate. And this also requires some new ideas. So let me briefly describe what you do in the classical case. So morally, so if you want to prove a linear estimate that E of f, the L2p norm, that's what you want to bound, you can write it as E of f squared, and then you take the LP norm of that to the power 1/2, and you can also write it as the bilinear extension operator E of f tensor f. You take the LP norm where E of f tensor g is just E of f times E of g, right? So this is just a nice notation that nothing else is. And then, so in the classical situation, what you try to do is you want to decompose the domain of f tensor g sort of away from the diagonal, some kind of Whitney decomposition adapted. You want to take boxes on which, so that on pairs of boxes U1 and U2, you have the right transversalities and you can control estimates, right? That's the idea. And so these are these kind of Whitney boxes which I have explained before. So, so you do this kind of decomposition into these kind of functions f sub mu and g sub mu, and f sub mu sits in one box of the first type u nu 1, and the g sub mu in another box u to nu, or let's say of the second type here. And so morally then you can look at this extension operator E of f tensor g. So this is morally is just this expression here. Okay. And the point is, of course, for each term we have a good bilinear estimate, but you cannot just simply sum them. I mean, this is too rough. You need some orthogonality arguments again. And for that, let's also just have a look at what happens in the elliptic case. So in the elliptic case, so we want to sum over all these pairs u1 nu, u2 nu. As that in our case, just imagine you have lots of such pairs here, and then group things together. And so in the classical case, in the elliptic case, the first step is that you want to prove, so this is the bilinear extension of f tensor g. You want to estimate this p norm to the power p by the sum of the p norms to the power p. So there's also some kind of decoupling or whatever, how one would call it, right? And this is done, of course, by interpolation. And of course, what one really uses and exploits is the fact if you take these boxes here in the elliptic case, which are just square boxes and which are sort of not too far apart, the sum of these two boxes, and these are the sets E sub nu, so the sum of these two boxes, they're again basically squares of size, let's say 2q times 2q, and they have a bounded overlap. So they're essentially pairwise disjoint. And that allows you to use Fourier multipliers which localize to those boxes in a smooth way. These are these operators T E sub nu. And so these boxes contain the support of the convolution product of f nu d mu and g nu d mu. And since they are pairwise disjoint, so this expresses the, this gives, of course, clearly a good estimate on L2, but to get L1 estimates, what you really need in the end is that these Fourier multipliers T E sub nu have uniform bounded operator norm on L1. And for squares, this is trivial. By rescaling, you see that you get uniform bound of these multipliers. Think of a Fourier multiplier which is essentially a smooth version of the characteristic function of some rectangle. Then, of course, all these inverse Fourier transforms of the multipliers have uniformly bounded L1 norm. So this is trivial. Now, in our case, this poses a problem. Because, remember, one of these boxes is a curved box of dimension delta times 1. And if you take a Fourier multiplier, which is associated to such a curved domain, it's easy to check that the L1 norm grows like delta to the minus 1/2. That's bad. So that really would destroy everything. So this argument doesn't work. So that's one point. And so what really, in the end, saves the day is that we further decompose these curved boxes into delta times delta squares. I think it's fine. So we further decompose those into squares, right? And then, correspondingly, we decompose our function, which is then I will show you a picture soon, into functions f sub I. Now maybe I should first show you the picture, and then draw the picture. So what we do, so suppose our function is supposed to be supported here. So we have, these are all delta times delta squares here. So we chop everything up into a grid of delta times delta squares. And so f sub ij is supported in the ijth delta square here. And f sub I is the sum along some row of these f sub ij. Then for each of these squares here, you have a corresponding curved box, because these are the pairs of transversality boxes, right? Where the transversality is of certain type. And so accordingly, the G sub ij is the curved box corresponding to f sub ij, right? And as I said, what we do, we further chop up these curved boxes into squares. So that means each function G sub ij is decomposed into the sum of G sub ij k. And k indexes which square box you choose, right? So that's the idea. And so maybe maybe I don't draw a picture. I hope you can roughly keep the picture in your mind. So each Gij is decomposed into the square. These functions G sub ijk supported in some square boxes. And then again we look at the contribution. Let's say for the situation where the parameter rho, which was the distance between y1 and y2, is of size 1. I mean, otherwise you rescale, right? So suppose we have this situation where the vertical distance is of size 1, like in this picture here. And so by E sub delta of f tensor G, I denote the corresponding contribution of the bilinear extension operator. And now you see, if you go back to this picture, if you go here through one row, the corresponding supports of the G sub ij fill out a large portion of our coordinate space here, so to speak. And if you pass on to another row, the same happens, only these curves change a little bit, the orientation and so on. So there's a high overlap of these curved boxes. That's a big problem. For each row, I mean, there's a lot of overlap. But the interesting thing, and that saves the day, if you take now two of these two little boxes here and take the sum, and if there's an overlap in the xy coordinate space, it turns out that on the graph, in the third coordinate, they are separated. And so this separation in the third coordinate saves the day. And so, and that's a key observation down there. So you should think that R3 is sort of chopped up into little delta cubes, and the supports now of these sums of the little pieces are essentially supported in cubes of size delta. And then what you can do, you can even improve the previous classical estimate by using an old result. If you take a little Petty square function where you replace the Haddock intervals by equidistant intervals, then at least for p bigger than 2 and finite, you still can estimate the square function in terms of the LP norm of the square function in terms of the LP norm of the function itself. So this goes back to Carlesen and independently to Cordoba, was even generalized to arbitrary intervals by Ruby de Francia. So using that result plus duality, indeed what we can prove is this improvement, that this part corresponding to this level rho equals 1 of the extension operator, the bilinear extension operator, can be controlled by this little L2 sum in I, j, and k of these functions, and then the LP norm of that. And since our p is close to, let's say, 5/3, so p/2 is less than 1, so you can pull in some of these things by, so it's a trivial estimate, and so you can group things together. The first sum over the k, so you sum back these little boxes which make up one of the curved boxes, right? So the k is a parameter which indicates where you are here. And so you first take the square function corresponding to these k's, and then you try to estimate the rest. And now comes the point, now this allows to go back to the curved boxes. Because if you think of these little L2 sum, you can think of the randomization by Khinchin's inequality. And so using Khinchin's inequality, each of the terms is controlled by, if you take for arbitrary sequence of signs epsilon k plus or minus 1, the sum of the epsilon k times g I j k. So the only difference is you put some signs here on the different boxes here, but the LQ norm is the same, so we can just assume that the sign is 1, right? And so we can come back to our curved box. And so in the end, it just suffices to control, in the end, it suffices to control those norms. And as I said, we can assume all signs are 1, and so we are back to the Gij. So, and that way, now we can use our bilinear estimate, which we had done before for the curve, for the pair, or let's say, of a function living in the curved box here and the square here. So we apply this bilinear estimate, and that gives this estimate here. And as I said, the Gij is now supported in a curved box. The Fij is in a horizontal box, right, of thickness delta. And we pick up this power of delta here, right? Now, the next step, the standard, since we want LP-LQ, we use Hölder's inequality to control the L2 norm here in these pieces by the L2 norm by the LQ norm. You should think of, let's say, P is 5/3 and Q is 5/2. That's roughly what you should keep in mind. That's a limiting situation. Okay, using Hölder's inequality, you pick up some other exponent here, and then you can estimate by the LQ norm here of Fij to the power p and Gij to the power p. Then the next step is we use just Cauchy-Schwarz. So the sum here in J is just brutally estimated by Cauchy-Schwarz. So we arrive at this estimate where we pick up the power 2p here, and again here the power 2p. So we sum the Fij in the LQ norm to the power 2p here, and here the Gij, the LQ norm to the power 2p. Okay, so just Cauchy-Schwarz. So, but now one can observe also that the 2p is bigger than 3, and so from, as I said, imagine p is 5/3, q is 5/2, and then you figure out that 2p is bigger than q, right? And so that allows to estimate this exponent, this little L2p sum by some little LQ sum, right? And so you sum up the little LQ norms of the Fij over all j, and the similar for the Gij. So that's why you can pass now to the sum of the Fij over j here and the LQ norm of that, and here the sum of the Gij takes the LQ norm of this sum. Okay, and now from here on, so remember the Fij, so there were these horizontal decompositions. So Fi was what lives in one horizontal strip of thickness delta, and if you sum the Fij, then you get the Fi, right? And so we get the LQ norm of the Fi here. And here, morally, if you sum correspondingly the Gij, so this would mean that we have different curved boxes which are sort of almost pairwise disjoint, and you sum them up. So morally get G, or a big portion of G. So there's nothing better you can do than estimate the sum of those by the LQ norm of G. So that's why you pull out here, this is basically controlled by the LQ norm of G. And here you still have the sum of the LQ norms of the Fi to the power p. And then you just again, simply apply Hölder, you pick up another exponent. The number of terms, capital N, is just 1 over delta. So this is just 1 over delta. So you get a certain power of delta altogether. And then you get here the LQ norm of the sum of the Fij, which is just controlled by the LQ norm of F. So in the end, for this part here, this portion of our bilinear operator corresponding to scale rho equals 1, morally, we get this estimate. Well, but you easily check that this exponent here, if P is 5 over 3 and Q is 5 over 2, this is what we are interested in, is 0. So it just works out. So if you stay a little bit above, let's say below the critical line, you can sum up things, right? And at all scales, actually, in these estimates, and that's how we, in the end, get the linear estimate. But as I said, we missed the critical line because that would require much finer arguments, and we have no idea how to do that at this point here. But anyway, so I think this gives at least some glimpse of what changes geometrically when you pass from elliptic to hyperbolic situations, right? And of course, this is what we would like to do, is study more general perturbation terms. For instance, the next step would be that we could think not as a perturbation just a function y cubed, but we could take any function h of y, which is of cubic or higher order. And even that already imposes some problems. But here we were very confident that we may be able to use work by Fong, Stein, and so on local structure of polynomials. So there's a good chance that that can be done. But for general perturbations depending on x and y, things will even get more complicated. But still, I think we hope that we have learned a lot from this very particular example. So typically there you will no longer see that this one of the two lines curves is a straight line. So typically you would have maybe curved lines in both situations. But you can see the same scheme should apply. But technically we expect that there's a lot of things to be understood. But we hope that we eventually can study that. And then, of course, once one has understood that, we would like to pass to higher dimensions and to see what's going on there. Also, of course, one could try to see what happens with the polynomial partition method. I would pretty much expect that it also should work and also push down this 10 over 3 to, what is it, through 3.25 or something like that. But there's still a lot of air. Okay, so that's it. Thank you very much.